7 brilliant presentations coming up. So each presentation is going to be 7 minutes and not a second longer. And to help us get started, we have Chris Roebuck, who's going to be talking about Git. So Chris, your 7 seconds will start as soon as you start speaking. Good luck.
7 seconds, better go quickly then. Thanks, Tom. Okay, yep. So I'm going to be introducing Git Going, my Git project template for LabVIEW. So inspiration from this, basically making things easier and increasing adoption of new features. So for example, the bookmark feature, I created a project provider to make the bookmark feature more accessible. My reason for that is to reduce context switching. I know anytime I have to switch context and leave LabVIEW to go and do something or go into a different window, it's just an excuse for me to start Googling cat videos. So if I can stay in the LabVIEW project or in the LabVIEW environment longer, then that's beneficial. Also, at the LabVIEW Architects Summit in Poland, I had a conversation with Sumida from NI, and we got talking about integrating Git directly into the LabVIEW environment and how we could go about that. And we bounced a few ideas around. Going back to last year, there was a presentation by Greg Payne, link on the screen, thanks Greg, regarding source code control tools, adoption rates, and usage in LabVIEW. On the left, we've got the adoption rates. We can see Git is the blue line, increasing rapidly, SVN, the red line, decreasing, and they crossed each other about 2012. Correspondingly, in LabVIEW, we don't see that rapid adoption of Git. Why? So I started to ask people in the LabVIEW community why, and I got a lot of answers. Some of them, Git is overkill for what I need. I don't need no stinking branches. The Managing Software Engineering in LabVIEW course only covered SVN. It scares me half to death. What if we could lower the barrier to entry for new Git users and give them some tangible benefits too? How do we make things easier in LabVIEW? We've got the project template wizard to help us automate and build projects from scratch. My objective to create a new project already under Git control, facilitate the creation of a Git ignore file, facilitate the use of branches, make it easy to publish to a remote, and even get started with continuous integration pipelines locally, such as running VI Analyzer and VI Tester. Also, we could show other LabVIEW users how we can extend the LabVIEW environment. So, getting started. Once you've installed Git Going, you've got a new LabVIEW, a new create new project wizard. We can select create new project with Git, and that takes us to the first page of that template, of that wizard. The first item is to allow us to create a Git ignore. By default, this is selected, and .lvlps, .aliases, and .exe have already been added for us, but of course we can add new items or specific files to be ignored and not tracked by Git. The next tab is the workflow tab. Here we can choose our branching scheme that we wish to employ when using Git. The first is basic. This will just create as a single branch, add our project code to that branch, and make the first commit to us. An alternative workflow might be to create a feature branch. So if we click on the drop down and select feature branch, that allows us to select a feature branch to develop, which will be branched off of master. We can give it a custom name, and there's some helpful information on the right just explaining what's going on. Alternatively, we could select Git flow and create a name for the feature that we're actually developing right now, but whilst also creating a develop and a master branch. If we wish to publish to a remote, let's say our Git repo is hosted on Bitbucket or GitHub, we can optionally configure Git to allow that code to be pushed to the remote. We just simply tick the box and add in the URL of the empty remote repository that we wish to push to. And finally, integration. So we have the option to enable a pre-commit, an action that is taken as we hit the commit button. In this case, we might want to run VI Analyzer or run VI Tester. So we can actually specify a particular VI Analyzer CFG file. So let's see that in action quickly. So here I've got an empty folder. I've got a VI Analyzer CFG already and a file that will fail that CFG. I'm now going to go ahead and use Git Going to create a new project already under Git source code control. So I've got a Bitbucket repo also, so I can show pushing to a remote. My repo is currently empty. So let's go through the wizard. So I'm going to stick with the standard ignore options, LVLPS, aliases, and .exe. I'm going to select a location where I want my new project to go. And let's go and have a look at the workflow now. Let's select the Git flow workflow and give our feature a branch name. So video goes slower when you're talking fast. Let's add a remote. So here I've put the URL of my Bitbucket remote, and let's also go ahead and enable a pre-commit. And in this case, when I commit code, I want it to run my VI Analyzer CFG. So let's pick that CFG. I'm not going to bother running VI Tester. Let's hit the finish button. Now, when we have a look on disk into our demo folder, we'll see what has been created. So we've got a project, an empty LabVIEW project that has been created. If we look on disk, we can see a Git folder has been created with a gitignore file. It's got our LVLPS aliases and exe extensions added to it. We can now see the status of our local Git repo. So let's do Git status. We can see our branch is up to date. The empty project and the ignore have all been committed. Our working tree is clean, and we can see the 3 local branches that have been created. If we now go to Bitbucket, we can see our empty repo now has the project, the gitignore, and the 3 branches have been created on our remote as well. In addition to this, this comes with an API. So if you want to build some of your own stuff on top of this, GitGoing installs a Git API. Okay, it's nothing fancy. It's just wrappers around system exec calls, but it installs this into the palette as well. What's coming next? A project provider for Git. The video is longer, by the way. If you want to watch it later, you'll see this continuous integration as well. It's coming soon. It's been submitted to the LV Tools Network, and the pre-release code is on GitHub. You can take a look at the URL there if you want to grab that. Thank you.
Awesome, Chris. You were within 2 seconds. So, congratulations.
Thank you.
Your tool's looking really, really good. I'll download it off GitHub and have a go with it myself.
Great stuff.
And I'm pleased that we're both using Gitbucket, and so hopefully I'll be able to copy exactly what you did.
Yep, although I should say, if you watch the video is 8 minutes long. You'll see me also push to GitHub and GitLab.
Awesome, that's really good to know.
Thank you very much, Tom. Thank you very much, GLA Summit organisers.
Awesome. Hey, Malcolm, how are you getting on?
Fine, thank you. Can you hear me and see me?
Awesome. We can see and hear and see your screen. So, again, 7 minutes for you. And I'm looking forward to our trip to McDonald's. Off you go.
Right. Well, thank you very much. So I want to talk today about how a trip to McDonald's can help you learn LabVIEW OOP. So hang on. That's not good. Oh, there we go. So this really is aimed at people who've never tried classes because they think they seem to be too complicated. I want to show you that really you only need to learn 4 things about classes to get started. There's hundreds of things you can learn, just these 4 things to get you started: encapsulation, inheritance, overrides, and dynamic dispatch. Now they can seem quite complicated processes, but the easiest way to learn is by taking a trip to McDonald's. How are we going to do that? If you think of a quarter pounder, a Big Mac, filet of fish, you think all the sandwiches at McDonald's are different, but actually they're all the same. They've all got a bun, they've all got a main filling, they've all got a topping, they've all got a relish, and they've all got a wrapper. So they all follow the same basic recipe. So they're all the same, but different. So McDonald's is using classes. McDonald's top level class is the sandwich. So the ingredients are the class data, and the cooking times and the preparation methods are the class methods. So if you add and ignore something, that's your override. So for example, you might ignore putting cheese on for a normal burger. So how does McDonald's work? The order comes into a grill team member. They substitute the generic recipe with the specific recipe for that sandwich. And in real time, they select and ignore ingredients and cooking times as required. So how does this relate to classes? Well, a fixed set of operations for fixed ingredients, that's encapsulation. They're all the same but different. That's inheritance. They're all inheriting the same parameters. Adding in or leaving out various ingredients, well, that's your overrides. And substituting as you go, that's dynamic dispatch. So if we had a generic recipe for an instrument, how would that help us? So first of all, think about an instrument being a power supply, a signal generator, a spectrum analyzer, but it also could be, it doesn't have to connect to hardware. It could be a logging engine or an error handling routine. So normally I would set one class per instrument. When you're running, you essentially initialize the system. So you read your ini files, you connect to your hardware. That's usually less than 1% of the runtime. When you're running code, you're setting up outputs, you're analyzing inputs, you're publishing data around your system, you're logging data to a file, and that's what you're doing, 98% of the time. And then at the end, you close it down. You close down your hardware, you write your ini file, you tidy things up, and you quit your application. So how does that relate to LabVIEW? Well, the first thing we need to do is create our top level class. So we get to our project, we create a new class, we can call it top level, McDonald's clearly call it sandwich. And then we add a series of dynamic dispatch VIs. So this is where we're creating our recipe. This is read from ini file. This is set up output, analyze input, that sort of thing. But most of them are going to be no operation. They're just abstract, empty. They're just placeholders, really. So once we've done that, you then decide how many actors or engines you've got in your system and create a class for each one. And you then create an override for each child class. So for example, the top level class analyze input is blank, but clearly if you've got a spectrum analyzer, your analyze input will have proper code in it. That's how you create an override. LabVIEW lets you choose from a list of the abstract classes that you created in a top level class. So you code your override, you'd remove this little the VI in the middle, add your code in here and save it. So now you'd have a recipe. So your initialize might be read ini file, your initial conditions and connect to your hardware. Your run might be set up the output, actually send your output to the hardware, your input, analyze your input, broadcast data, log it, error handling, all those sorts of things. And then finally closing is disconnecting your hardware and finishing off. But if you look here, you may think, well, hang on, if I've got an output and an input, aren't they going to conflict? But this is where dynamic dispatch comes in. So if you run, that's where it would go through all of those. But if you had, I've got here, say, a chemical pump controller. So I'm setting up an output voltage, I'm sending an output voltage, but I haven't created overrides for input and analyze input. So what LabVIEW actually sees is this. In other words, LabVIEW is clever enough to ignore the overrides that you haven't created. So what are the advantages of classes? First of all, encapsulation. It keeps your code neat and tidy. That especially helps in very large projects where things can get all over your hard drive. Inheritance. All your code has the same look and feel. Just like in McDonald's, every sandwich has the same look and feel about it. When it comes to the overrides, you supply the ingredients and the cooking methods, and LabVIEW does the cooking. In other words, the dynamic dispatch is free in LabVIEW. It basically does it all for you. So what are the other advantages? All your VIs are simple and look similar. So you've got high cohesion. The class recipes knows exactly where you need to write and look for a specific piece of code. That's particularly useful when you're looking for errors. If you want a new instrument, well, you just create a new class and follow the same recipe. You use the same recipe again and again. So what about conclusions? Classes allow for consistent code. The 4 things you need to learn about classes just to get started are encapsulation, inheritance, overrides, and dynamic dispatch. And don't be afraid of classes. It's as easy as having a burger. And that's me done. Right. If you need to, there is some example code actually. If you want to contact me, or if you have any further questions, those are my that's my contact details. Thank you very much.
Sure. If anyone has a very quick question, you're welcome to ask it now. We have about 20 seconds. I don't see any in the chat. Okay. Well, thank you very much, Malcolm. Okay, next up we. Thank you. Next up, we have Christian. Christian's just joining us now. So Christian, we're in for a double treat here. He's going to give 2 presentations. So Christian, I'll give you 14 minutes to talk about adapters over interfaces and 7 things you can't do with LabVIEW and Docker.
Great, thanks. So I'm hoping that the most egregious thing about this presentation is going to be the title, taken in an English language formulation. Of course, it is a form of source code control. And so I would like to, re-highlight the kind of capitalization and point out that I'm talking about the idea of a parent-child relationship, and there is when you have 2 classes and one of them can be a parent and one of them can be a child. And so in this case, the parent that I'm talking about is the source code control API that Chris Cellino has available at this Bitbucket link. And so it was suggested to me that this Bitbucket link and the API here could be used as part of a CI system or some kind of build operation to enable different source code control providers to be used depending on whatever was required for a given package. And so the API is mostly designed for Perforce, but we wanted to look for a Git-based version. And so I started and had a look at this API, but the Perforce API doesn't particularly fit the Git kind of idea. So I decided that in order to write something for users who were more familiar with Git, I would first write a library that handled the Git operations, and then use an adapter from like the Gang of 4 adapter pattern to fit the Git API into the source code control API. So the code is not particularly special or exciting. The core of the Git implementation class is this execute command VI. And so this handles some file path formatting with the dynamic dispatch VI. And if you were to include a kind of conditional disable structure around here, you could probably make this cross-platform. This is only tested on Windows at the moment. And here is an example operation of the kind that we might see in the Git API. So here I'm doing clone, and I'm going to manipulate the top directory, which is used as the working directory of the command, and pass in some Git operation and handle the parameters. And so the goal here is not to provide a kind of comprehensive Git API, but to provide all of the kind of things that you would want if you were using it for a build system or CI, some kind of automated use of a Git API. And so there are only a limited subset of the options. And these are the things that I thought would be useful, but I am open to alternative suggestions or modifications. Stefan Lemons already gave me some great suggestions of other commands that would be useful. And so I'm planning on putting those in the fairly immediate future. Here is the idea of the adapter pattern. And so I don't have the documentation for the SCC API on a slide, which was a mistake, but there are some that are quite easy to adopt. So the submit VI, for example, is almost exactly equivalent to git push. And git add and git reset also have equivalent files with their change list, add and revert. But others are a little bit more complicated. For example, sync requires probably a checkout and a reset, or alternatively, perhaps git checkout with force, which will overwrite files in the local directory. And taking a snapshot maps quite closely to git tag, but requires some additional help from reset, add, and commit, which is what you're seeing in this lower right-hand corner here. And so that forms kind of the basis of this idea. It's not overwhelmingly complicated, and I'm going to move a little bit of time into my next presentation, if at all possible. So if there aren't any questions, thank you, and I will shuffle over.
You still have about 10 minutes left, Christian.
That I think will be perfect. I hope. We'll see how quickly I can do a demo. And so I know there's a lag between the time that I say something and the time that you hear something. And so I would like to ask if people could give me a numerical operation that takes 2 inputs and produces 1 output and is available on Linux RT. And there we go. So I'm going to start with something that you can do on in a Docker installation with LabVIEW, and that's install nipm on a clean computer from the command line. So here we have my Docker file for building basically the nipm installation, and I've just highlighted the kind of section that calls the invoke web request, which is a PowerShell command, and it will download a file that's passed by argument, and then runs the installer with some command parameters. And so this is one Docker file that can be used to create a kind of base image. However, to install things like LabVIEW, you have to be able to add the feeds that nipm uses. NI Package Manager handles this kind of transparently, but if you want to do it from the command line, you need the uniform resource identifiers, and there isn't an easily referenced list of these available that I am aware of. And so you need to essentially use a computer that already has a working nipm installation in order to be able to get these values. And so that's what I show here. You can use the nipackage list command to kind of match a name-like thing and get the actual package name that would be installed. And then you can use list source feeds and the name of the package that you just got to find out the source package repository name. And so then when you add this feed with the previous command, feed add, you can update with nipackage update and then install the packages quite easily using the command line. Unfortunately, there are some packages that don't install directly from nipackage, and these tend to fail with a message that looks kind of like this. So you have some packages fail to install with errors that say error minus 125,530 or something similar. An error occurred while installing the MSI at something 64.msi. And fortunately, most of these aren't packages that we care about for automated build. I suspect that not having them means that things won't run in a Docker container, but I'm not trying to do that. I only want to be able to build things in my Docker container and then have them run if I put them on another computer that had working driver installations. And so I go from there to, instead of copying files from a working computer, creating fake replacement packages. So it's been suggested to me that you could, for example, install DACMX by copying the VIs from vi.lib into your Docker container. And I'm told that that will work, but I didn't have much luck doing it myself. I tried using folder changes view, which will generate a list of file system changes, but associating them with a specific package or trying to work out which ones I needed to copy was a little troublesome for me. And so instead, I decided it would be easier and perhaps more reproducible for me to create fake NI packages with no contents and then just pretend that their dependencies were satisfied. And so here I can see that NI LabVIEW 2019 RT module x86en, which is the RT module, will install with no problems through NI Package Manager and the NI Package command line, provided all of the dependencies that it has are already installed. And some of these dependencies have the error that we just saw on the previous slide. And I had to create 11 fake packages, of which 5 are listed here. One of them is the FPGA driver, which I strongly suspect means that if I was to try and build FPGA code, it wouldn't work. But for RT and cRIO and DACMX, this was enough for me, almost. Bringing me on to my next can't point. which is essentially that you can't manage to fake DACMX in quite this way. As much as I tried, if I didn't have anything from the NI DACMX runtime core package, then my libraries or projects that contain DACMX code just wouldn't load in the Docker container. And so this was a little bit unfortunate, but you can get around this by manually extracting the DACMX runtime core, the real package, and then running the MSIs inside. And so this bit is a little bit untrue, but I'm going to continue with it anyway and explain on the next slide what I learned since yesterday. And so all of the failing MSIs are 64-bit versions, and the ones that don't contain 64 in them will install just fine. And so I haven't tested the behavior in 64-bit LabVIEW, so I suspect that this might be a little bit of a train wreck. But unfortunately, I don't know if this train crash has a conveniently placed whale. And so you can build simple applications for desktop. You can build applications that use DACMX, at least for 32-bit. And so clarifying on that previous point, I heard from Aaron Pena yesterday that probably the core contents of the DACMX driver are in the not 64-bit labeled MSIs, and that there are 32-bit labeled MSIs that just don't download on my computer. And so perhaps the 32 and 64 state of install is equivalent. So you may also be able to do this for 64-bit without problems, but I haven't tested that. And you can build applications that execute on RT. And now I have 4 minutes left, well, 3 minutes and 20 seconds. So I'm going to check the chat and see if anyone has a example operation. Nobody wanted to give me a mathematical operation with 2 inputs and 1 output. That's unfortunate. I'm going to go ahead anyway. And so, GERD, I strongly suspect that FPGA is not supported. I haven't tried compiling FPGA on a Docker container. I had enough trouble getting it to run in a virtual machine. So I'm sorry, but probably not. So here is my, no, that's not what I wanted. Here is my remote desktop. And I have a real-time project. It has an unconfigured Creo 9045 with main VI. Stefan wants add, so I'm going to modify this and just replace it with add, which is convenient. And then I'm going to close this, and I'm just going to close this project, and it's going to build into this directory, essentially. And I don't need that anymore. So here I have my Docker container, which is already open. Maybe I should close that. So I can run docker exec and open up my container that's already running. And then I want to change directory into my shared directory. This is just here because it's more convenient for copying files backwards and forwards. And this is the command using James McNally's LabVIEW build and the GCLI tool to produce an appropriate output. And given about 20 seconds, which I'm hoping I still have, this will build. Yes, I've got about 1.5 minutes, I think. So this is starting a build, and it's going to finish a build very shortly, I hope. There we go. And so now if I go into here and scroll down all of these many folders that you get on RT, I have this, which was just compiled now. And I'm going to copy it off my real-time system, get rid of that, and open up Internet Explorer. I will log into a Creo that's sat next to me. Sadly, it's missing almost all of its modules because they were more difficult to take out of the lab. And, oh, I need to paste that file somewhere. So I'm just going to delete this and paste my new RT executable that I just compiled, and I will upload here. And now restart my Creo. Switch back here and hope that I have enough time to connect to it. 15 seconds. I'm thinking this is unlikely. Maybe I'll be granted a brief momentary respite. the light's gone off on the serial. It's come back on. And now I'm just going to frantically click refresh and hope. I'm getting status lights. Come on. Not quite fast enough. Sometimes it feels like you'd have to change the IP address. That's frozen. Back to this and move my application over here. I should be able to see that my VIs add and subtract. And that's the end of my demo and everything that I had to say. So thank you for the extra time, because I'm pretty sure I won't see you.
No worries. Thank you very much, Christian. I'm currently in the process of refactoring my build routine and my source code control and all of the code management side of things. So your presentation definitely gave me food for thought. Next up, we have Michael. Michael, are you here? Awesome. So, Michael, I believe you're going to be talking about analytics and big data stuff.
Not so much about analytics and big data itself, but more about the common problems that we are sometimes facing when we are asked to do stuff that will present this data. Because first of all, I would like to go with our giants are female, because that's something that I really like to share with everybody. Here, I would like to point out to Andrea Ghez, who is a professor at the Department of Physics. She won a Nobel Prize for a supermassive compact object in the center of our galaxy. You got it, it's a black hole. The core issue I want to face in here is that sometimes we are asked to create a simple app just to collect and save data. But we want to have those data appearing most likely from hardware at asynchronous rates. And we want to view it live and inspect it later, and then have a total historical view as well as division by experiments or runs. That's not easy. LabVIEW is not the best tool for that. When we would just want to view it live, we tend to end up in kind of not the nicest front panels if we do it in a rapid way, which does not give a full control for the user. Or we put a lot of effort in making it beautiful, but that's a huge request or a huge workload to do so. If we want to inspect it later, we are having LabVIEW gives us a fantastic ways of saving data to TDMS or to CSV. However, TDMS is fantastic when it comes from LabVIEW control. Users are not so happy, especially those who just want to have some ad hoc data. CSV, on the other side, gives a full power to the users, but they need to use their powers. Apparently, what I learned, they don't like it as well. What is the solution? It's a database. We can throw stuff to the database, and we have a number of options to do so. We can go with classic PostgreSQL, MySQL, SQLite. Plenty of those databases are available, which will help us to store and then retrieve data. However, often what we are being asked is actually to look for time series databases. It's a new type of database. Usually they are not relational. One of the main feature is that they are optimized for storing and serving time series. They are having way quicker response times, and the optimization allows for mostly being able to render data sets very quickly. One of the examples of such database is InfluxDB. It is an open source major project since started about 2013. It provides simple line protocol to push the data into the InfluxDB. It has out-of-the-box Docker installation, and it has a seamless integration with Grafana. What is Grafana? Because here I mentioned about where to store data. We want also to see data, and we can also analyze and monitor them. Grafana is an open source multi-platform solution with intuitive codeless integration, which has a free version to start up, and there is an enterprise version that gives you a lot of support and custom branding, so you can make your visualization very, very nice. It supports various backends, including InfluxDB, and it also has out-of-the-box Docker installation. I have prepared here a walkthrough with exact steps to recreate a system I have. It's available on GitHub, and I will just throw this in a link later on in here. Here, I would like right now to execute this command I have just put on my Ubuntu machine with a Docker installed. I already downloaded the images, I need to say, just in order to save some time. I just run a Docker in here, and it allows me to open a Grafana, which is a tool that we will be able to use for visualizing, as well as Chronograph, which is a tool to view the data in the database live. How it links to LabVIEW. LabVIEW can have a simple app that is just throwing data, and of course, this one is not running correctly. Yes, it creates a simple data with asynchronous rates, three different rates, three different types of signals we have in here. And what it does, instead of saving it in the CSV file, we are using a line protocol, which is a simple implementation of a post command with simple syntax. What I will do now, I will just navigate to Grafana and create a dashboard. I will just add a new panel. Here, I will show you how simple it is, because I already have a default measurement. Test 1 is the measurement created in my line protocol. I have called it test 1. And I have value of signal A, signal B, and signal C. I can quickly see those values, but without even trying to build up the whole dashboard. So we can quickly visualize and look at individual pieces. I have right now created also I have a preset view where I have created all those three signals, which should be equivalent to what we see on the main window here of the data created. We are having a sine wave and some sawtooth signals. Grafana is a very nice tool, as we can quickly inspect this data, change the timescales for some preset values. And I think my time is over, so I will not go into live demo. However, it's also easy to look at the production code when we can have multiple graphs, multiple layouts laid off on top of each other. Thank you very much. All questions, please go in private on that. Thanks a lot.
Awesome. Thank you so much, Michael. Interesting stuff. Right. Next up, we have more fun with hardware with Aaron, who's going to be giving us a great demonstration. So, same rules apply, 7 minutes. So, looking forward to it. Are you ready?
I'm ready. Thank you. So I'm going to talk about forcing the use of forcing CRIO and CDAC for hardware state simulation. This is a feature that not a lot of people know about and only works if you actually have, if you're in scan engine mode, not if you're doing FPGA mode. And so with the forcing, you're able to override the inputs and outputs for scan engine.
Welcome back, Aaron.
Thank you.
Ready to take over?
Not what I was expecting. So with compact Rio devices, if you have the FPGA in scan mode, you can actually directly access the I/O. Sorry, bad echo there that I needed to fix. You can access the scan mode through the NI Distributed System Manager, or LabVIEW also provides an API for you to access the data. If you use Distributed System Manager, you can come in and look at your systems, and you enable forcing at the network module level and individual channel level. When you start forcing a channel, you can set inputs or outputs, whether they're analog or digital, to a specified value. With a input, you're going to see whatever value you've typed in. So for buzzer off right here, if I set it to true and click force, any software reading this channel will now see a true input. If it's an analog, I can set it to 1.34 volts. So in order to simulate my customer system, when I have the compact Rio modules, but I don't have the actual hardware that everything would hook up to, I built in the ability through the LabVIEW API to override my I/O. And so this panel shows the current state of all of I/O. We have a number of things that are showing as invalid, certain things showing off, certain things showing open. I can apply a preset to my channels that will put the system in a known good state. I can also, through this little tool that I created, come in.
Yeah. I'm not sure how much time you have left. Let's just say you have an extra 5 minutes.
That's fine.
Talk us through what you're doing.
Yeah, so what I was attempting to show before I blue screened for my third time in the last hour when I haven't blue screened in months was I created a little utility that has a bunch of predefined states of the system. And so I can choose a particular state to put the system in that mimics part of its natural state when there actually is hardware. And so when I tell the system to exercise different functionality, I created an API into that so that not only did I have manual control, but the system would tell that little control program what it was attempting to do. So the control program would put the I/O in the state that it was expected to be in. Now, this is good and bad because I can create bad states deliberately. I can create good states deliberately. But one thing you have to be careful of when you're using forcing is that if you force the outputs go to that value. So if you're driving motors, if you're driving heaters, you're bypassing any of your safety, any of your interlocks. It can be very useful for hardware debugging, but it can also be dangerous. In my case, it allows me to simulate my customer's huge system while only having the CRIO and not the hundreds of sensors that they actually have. So I apologize that apparently between Hopin plus my VMs that my video driver does not like that. But I was able to show you at least a little bit of it.
Awesome stuff. Thank you very much, Aaron. And I'm sorry you had that hat trick of blue screens in your 7-minute demo. Cool. So as I said, Hopin's going to be open until 2 o'clock and UTC. So even after the final session, if you want to hang out with your new colleagues, people you've networked with, please feel free to use Hopin, find yourself a meeting room. Okay, up next in 5 minutes, we have 3 sets of sessions. James McNally, we have Future Promises, Borrowing Ideas from Asynchronous Languages. We have Nathan talking about FPGA, computing algorithm for neural networks. Then we have Pravin talking about online video compression for ADAS recording systems. I'm not sure which one to choose. They all sound so good. Right, I'll stop talking. Have fun, everyone, and I'll see you again soon.